Hello good people, I'm going to explore the Lewis dot structures of covalent compounds. I have listed 4 pairings: hydrogen and chloride, sulfur and oxygen, phosphorus and nitrogen, and finally carbon and oxygen. I aim to determine the structural formula for each of these pairings. Before I do this myself, I invite you to try doing it on your own. To help you with the task, here are the 5 steps that I recommend you follow. Firstly, draw the Lewis dot structures of individual atoms. Then, based on the number of single valence electrons, determine how many covalent bonds does each atom want to form. Next, determine or circle the bonding pairs of electrons. Once you have done that, replace each bonding pair with a line. And finally, draw the non-bonding lone pairs of electrons. So pause the video and have a go. The first thing that I'm going to do is draw in the valence electrons for all of the atoms present. So let me quickly do that. And now I'm going to begin with the hydrogen and the chlorine on the left side of the screen. Based on the number of single valence electrons, both hydrogen and chlorine want to form a single bond. And it is those single valence electrons that will be shared. So these 2 electrons that I'm circling in orange, they will form a covalent bond. Let me rewrite that a little bit neater. So now, from the point of view of the hydrogen, it has the electron configuration of helium, and from the point of view of chlorine, it has the electron configuration of argon. The shared electrons can be represented as a line between 2 atoms. So here is the hydrogen, then a line, and then a chlorine. And now I can also add all of the lone pairs, and here they are. What about sulfur and oxygen? Both sulfur and oxygen have 2 unpaired valence electrons. This means that they will both aim to form 2 covalent bonds. So in this case, I could say that these 2 electrons will be shared, and then these 2 electrons will be shared as well. Let me draw this sharing of electrons a bit neater. So now, 2 pairs of electrons are being shared between sulfur and oxygen. I can write S for sulfur, then 2 lines representing a covalent double bond, and then oxygen. I can also add the lone pairs of electrons. So here they are. Moving on to phosphorus and nitrogen. Based on the number of single valence electrons, both phosphorus and nitrogen would like to form 3 covalent bonds. So I could say that this pair of electrons will be shared, also this pair of electrons will be shared, and then this one as well. So let me just circle them in. Here we go. Again, I'm going to rewrite this in a neater fashion. And now, 3 pairs of electrons are being shared between phosphorus and nitrogen. This means that between the symbol for phosphorus, P, and the symbol for nitrogen, N, I will have 3 lines representing a triple covalent bond. And let's not forget the lone pairs. So here they are as well. Finally, let's look at carbon and oxygen. This one is a little bit tricky. And once I'm finished, it will look as if though I have broken a few rules that I have established earlier. But in chemistry, we have rules and then a list of exceptions as long as my arm. So based on the number of single valence electrons, oxygen would like to form 2 bonds. Carbon, however, would like to form 4 bonds. So there's going to be a bit of a mismatch. But let's start pairing up single electrons and see what happens. So maybe these 2 electrons will pair up to form a bond, and then these 2 electrons will pair up to form a bond. Let me write what we have so far. Here is the carbon, and here is the oxygen. And here are the 2 pairs of shared electrons. What about the other electrons? Well, let me bring them in as well. So now I could say that I will have a bond because of this pair of electrons, and I will also have a bond because of this pair of electrons. So that will give me carbon, double bond, oxygen. And let us not forget the other electrons. So here they are, the two pairs on oxygen and the two unpaired electrons on carbon. From the point of view of the oxygen, everything is fine. It has two bonds and it also has 8 valence electrons. However, from the point of view of the carbon, things are not fine. It only has 2 bonds, whereas it wants 4, and currently it only has 6 valence electrons in its vicinity. This means it's time for an electron shuffle and a bit of a compromise. And the way we can talk about this is to say that the oxygen will donate this entire pair as a bond, and the 2 single electrons on carbon will pair up. And so we will end up with carbon, triple bond, oxygen. And to finish it off, I will still have the lone pairs. So here they are as well. From the point of view of carbon, yes, it has 3 bonds, whereas it wants 4, but at least it has 8 valence electrons in its vicinity. From the point of view of oxygen, it has 3 bonds, whereas it only wants 2, but once again, at least it has 8 valence electrons in its vicinity. It is a compromise. And as is the case with all good compromises, neither party ends up being truly happy. That is all for now, and I will see you on the flip side.